I am just another speck of sand. And the Earth, really, in the cosmic scheme of things, is another speck. And the Sun, an unremarkable star, nothing special about the Sun. The Sun is another speck. And the galaxy is a speck. I'm a speck, on a speck, orbiting a speck, among other specks, among still other specks, in the middle of specklessness. I am not, I am insignificant, I suck!
The question of questions for mankind, the problem which underlies all others, is the ascertainment of the place which mankind occupies in nature and of his relations to the universe. Thomas Henry Huxley, 1861.
For much of human history, man regarded himself as unique in nature. For ancient Jews and Christians, humans were viewed as created in the image of God, the crown of the created order. For Greeks and Romans, man was the thinking animal, whose rational faculties produced philosophy, mathematics, politics, and the arts. By the 19th century, however, a growing number of people were questioning man's special status. The questioning culminated with Charles Darwin and his theory of evolution by natural selection. According to Darwin and many of his followers, there was no fundamental difference between human beings and other living creatures. Post-Darwin, many scientists insisted that human beings were the result of unguided and impersonal laws that created everything else. But are human beings really the accidental byproducts of a universe that did not have them in mind? According to geneticist Michael Denton, the discoveries of science over the past century have pointed in a dramatically different direction. Denton's research focuses on locating genes responsible for inherited retinal disease in humans. This research led to the identification of the gene used in the first successful gene therapy for inherited blindness at Moorfields Eye Hospital in London. Denton has become increasingly intrigued by evidence from nature that man is not an accident. Indeed, according to him, the universe seems to have been designed for life like us.
The universe is fit for carbon-based life and fit for higher organisms utilizing oxygen. And that is not my view, that is the view of everybody working in the field of astrobiology and everybody working for NASA. This is one of the most important demonstrations in the history of science, because it means that in fact human form, human biology, has some sort of a special place in the order of nature.
Many features of our universe seem to be specially prepared to allow life to flourish. If these features were even the slightest bit different, life as we know it wouldn't just be harder, it would be impossible.
There are four fundamental forces in nature, according to physicists. These have to be almost exactly as they are to have stable planets, to have galaxies, and to have Earths like our planet, which lasts for millions and billions of years, okay?
If the gravitational force were weaker, stars or galaxies would not be able to form. If the gravitational force were stronger, the universe itself would collapse. If the strong nuclear force were smaller, the only stable element in the universe would be hydrogen. If the strong nuclear force were greater, there would be no hydrogen. Without hydrogen, there would be no water. Without water, there likely would be no life. The atomic elements needed for life to exist are produced inside the nuclear furnaces of the stars. But how do these life-giving atoms get from the interiors of stars to places where rocky planets like Earth can form? It's another amazing story of a universe that seems to have been built just right for life.
Well, nature has another trick up its sleeve. It's called supernovae. These are explosions when, in fact, for a short time, one star in a galaxy outshines the whole galaxy, and it explodes. To get the atoms out of the center of the stars, you have to blow up the star and distribute the stuff throughout the universe. The cosmos is seeded, therefore, through these supernova explosions with the atoms of life.
Supernovae have to occur in exactly the right way, or they will annihilate life rather than nourish it.
Conditions must be exactly right for the explosion of supernovae. Too many supernovae and there's no life in the universe. So these strange flicking fireflies of the cosmic night have to flick at just the right rate. Flick too fast, no life. It'll destroy all life in the universe. Flick too slowly, you'll have no carbon to build living things, okay?
The number of cosmic factors that work together serendipitously to make life possible has made a powerful impression on many scientists, regardless of their religious beliefs. Sir Fred Hoyle was a leading astrophysicist at Cambridge University. An avowed atheist, Hoyle nevertheless admitted that the evidence of nature itself seemed to point to intelligent design.
A common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics as well as with chemistry and biology. Fred Hoyle, Cambridge University, 1981.
The cosmos as a whole seems fine-tuned to make life possible, but so do three of its most basic elements and compounds that most of us take for granted: carbon, water, and oxygen. Carbon is the key atomic building block of all organic matter, the basis for the molecular machines inside our cells, for the petals of flowers and the bark of trees, for the antlers of elk, and for the skin of a newborn baby. Carbon has an enormous and unique capacity to form multiple yet stable chemical bonds, both with itself and with other elements. In theory, carbon can form a virtually infinite number of different chemical compounds. More than 65 million carbon compounds have actually been identified, with more being discovered all the time.
If you look at the properties of the carbon atom, it's the only atom in the periodic table, really, that you can build lots of a vast diversity of complex chemical compounds with. And I would assume that, like everybody else, like NASA and everybody now, that if you're going to build complex, self-replicating chemical systems, you're going to have to choose the carbon atom.
There is no other known element in the universe that can substitute for carbon. If carbon were to disappear tomorrow, complex life like ourselves wouldn't just dwindle, it would cease to exist. Carbon is especially fit to make life possible in the environment found here on Earth. That's because carbon compounds needed for complex life are only stable within a narrow range of temperatures. The range of temperatures that just happens to be found on our planet. If temperatures on Earth were higher, like on the surface of Venus, carbon compounds would no longer be stable, undermining both the creation and perpetuation of complex life. If temperatures on Earth were lower, like on Uranus, the chemical reactions creating carbon compounds would be so slow that life could not arise here for tens of billions of more years, if ever. Not only do carbon compounds make life itself possible, they make our current human technological civilization possible. From the vast cornucopia of carbon molecules that fill our planet, we obtain natural gas, petroleum, clothing, sugar, plastics, and anesthetics. Some have proposed that alien life forms might exist based on silicon rather than carbon. But most experts think that idea is the stuff of science fiction rather than science. In fact, the uniqueness of carbon has led one astrobiology textbook to suggest that if aliens were ever to visit the Earth, we should welcome them with carbon-based cakes rather than silicon-based rocks.
I came here to give you these facts.
Water is the driving force of all nature. Leonardo da Vinci.
It covers nearly 3/4 of our planet, and it's essential for our existence. Water is a thing of wonder and inspiration. It also happens to be uniquely fit for creatures like us. One key feature of water that promotes life is its capacity to act as a universal solvent. Water can dissolve almost anything. This allows it to be an ideal carrier of the many chemicals and minerals we need for life. At the same time, water is less chemically reactive than many other solvents. Sulfuric acid can dissolve minerals, but it also destroys them by reacting with them and making them useless for life. Water dissolves minerals without destroying them, allowing them to carry out their life-giving functions. Water is thus an ideal solvent for life. Another important feature of water that enables life is its low viscosity or thickness. Different liquids can have radically different viscosities. Tar has a much higher viscosity than olive oil, and olive oil has a much higher viscosity than water. Water has one of the lowest viscosities of any common liquid, and its viscosity seems just right to facilitate life like ours. If the viscosity of water were any lower, like the viscosity of liquid hydrogen, the delicate microscopic structures in our cells wouldn't survive when subjected to outside forces. On the other hand, if water's viscosity were even slightly higher, the pumping of blood through the tiny capillaries which permeate all the organs in the body would be impossible, and our circulatory system wouldn't be able to supply enough oxygen or glucose to our muscle tissues for organisms like us to survive. In sum, the viscosity of water seems to be finely tuned for life like us. But perhaps the most striking features of water that make life possible are its thermal properties, which help us deal with the impact of heat. Many biochemical processes essential for life can only operate within a narrow band of temperatures. If the temperature is too high or too low, these biochemical processes cease to function, and life like ours becomes impossible. Thus, maintaining stable temperatures on the Earth and inside ourselves is essential for us to exist. Water is critical to maintaining stable temperatures. Water has a high heat capacity, which means that it can absorb large amounts of heat with only a relatively small increase in its temperature. You can see this in everyday life. Walk barefoot on sand on a hot summer's day, and you'll likely burn your feet. Place your feet in a swimming pool during the same summer day, and the water will only be pleasantly warm. Water's high capacity for absorbing heat helps both our planet and our bodies to maintain a stable temperature range.
You have to put a lot of energy into water to change the temperature. That's very convenient. It means it's very easy for warm-blooded organisms like ourselves to maintain body temperature. So that's a property of water which seems specifically fit of beings like ourselves. And that there's another property of water which might even be more critical, and that is that in fact the evaporative cooling of water is one of the greatest of any fluid that's known.
The human metabolism produces large amounts of heat that needs to be discharged, or the body will overheat and die. The evaporation of water through perspiration is one of the key ways our body gets rid of excess heat. Water is especially fit for the task of cooling us because it absorbs a large amount of heat when it evaporates. In fact, more heat is absorbed by the evaporation of water than by the evaporation of almost any other known fluid at ambient temperatures and pressures. Water is uniquely suited to help us shed excess heat in hot climates. When the outside temperatures exceed the level of your body temperature, other ways of getting rid of heat won't work.
Because the only way to lose heat when the environment around you is reaching sort of 38 degrees centigrade is by evaporative cooling. Because you can't radiate the heat out because the environment is 38 degrees, it's warmer than you, right? So it's absolutely critical to warm-blooded organisms like ourselves that the evaporative cooling of water is very high. It's one of the highest of any known common fluid.
The high evaporative cooling of water appears to benefit humans more than any other animal. Being relatively hairless, humans lose heat through evaporative cooling more efficiently than any other mammal. Consequently, in the heat of the day, humans can exert themselves continuously for longer periods of time than other mammals. Another intriguing thermal property of water is its peculiar behavior when freezing. Most liquids contract as they freeze, making their solid form denser than their liquid form. Unlike virtually every other liquid, however, water expands when it freezes, making frozen water less dense than liquid water. That's why ice floats. This special property of water helps preserve it in its liquid state. If water acted like most other liquids, oceans and lakes would freeze from the bottom up until there was no liquid left. Most of the Earth would be permanently encased in ice, making life as we know it impossible. Instead, when ice forms on the top of water, it creates a protective lid that insulates the water underneath it from the cold, keeping it in its liquid state and preserving its ability to nourish life. Water makes our life possible not only through its own peculiar properties, but also through the way it operates in tandem with seemingly independent geological processes to recycle the elements required for life on Earth. Through the movement of tectonic plates and the action of volcanoes, the tectonic cycle pushes up to the Earth's surface the minerals and other elements needed for life. Then the hydrologic or water cycle dissolves these same minerals and elements through erosion and ultimately deposits them on the ocean floor, where the tectonic cycle can recycle them yet again.
And these are two great cogs which work together. The tectonic cycle keeps on recycling the crustal material, and the hydrolytic cycle dissolves the key minerals which are necessary for life and sort of takes them out of the crusts and puts them in the hydrosphere, in the fluids of the Earth.
By working together, the tectonic cycle and the water cycle preserve the chemical and physical stability of the Earth's surface environment, enabling life to continue to flourish.
During an emergency situation requiring the use of oxygen, the pilot should be able to release and don the mask within 5 seconds. Warning: masks have not been qualified for wear over beards or heavy facial hair growth in accordance with FAA technical standard orders. Facial hair that crosses ceiling surfaces can seriously degrade the performance of these masks.
Some living things can survive without oxygen, but not beings like ourselves. Oxygen is another element that is fine-tuned to enable organisms like us.
Constant activities of beings like ourselves require energy, great quantities of metabolic energy. And basically, the only atom in the periodic table that's capable of delivering this energy is oxygen. And we get all our energy by the slow combustion of hydrocarbons. It's the same as a fire. And it's not just me that's saying this. And what I'm saying is that, in fact, oxygen is the signature of complex life. If you're going to have complex life needing a lot of energy anywhere in the universe, you're going to have to use oxygen.
But for oxygen to be available for use, you need the right kind of planet and the right kind of atmosphere.
And you can only get atmospheres containing oxygen on planets roughly the size of the Earth. If they're too big, they retain primeval gases such as hydrogen and helium. If they're too small, they lose all their atmosphere. So you have to have planets roughly this size.
Getting the oxygen we need for life involves a stunning series of coincidences. On our planet, plants utilize the energy of sunlight to manufacture sugars and other essential organic compounds by a process known as photosynthesis. Photosynthesis converts radiant energy from the sun into a form of stored chemical energy that plants can use. But along the way, photosynthesis also generates an important waste product: oxygen. In other words, the same process that supplies the energy plants need just happens to also produce a waste product that supplies energy to humans and many other animals. If that weren't amazing enough, photosynthesis must have access to just the right kind of energy in order to work.
And what energy does the photosynthesis need? It's the very small region of the electromagnetic spectrum, which is the visual region. This is the region which powers photosynthesis. In fact, it's light energy. Light energy has the correct characteristics to raise the atoms of organic chemistry to levels for chemical interactions. So light is the right electromagnetic energy for photosynthesis. When you look at the sun, you find the sun turns out nearly all of its energy in the visible spectrum. So the sun is pouring out just the energy you need for photosynthesis. And so the radiant energy output of the sun happens to be in exactly the same region of the electromagnetic spectrum that you need for photosynthesis.
The Earth's atmosphere has just the right composition to allow the visible light we need to reach the surface of the planet, while largely absorbing many other kinds of radiation that are dangerous to life.
There are an awesome set of coincidences in the atmosphere which happen to allow the light of the sun to come right down to the surface of the Earth, where it can empower photosynthesis, where miraculously the atmosphere blocks out lots of other forms of radiation and allows the life-giving light to get to the planetary surface to allow photosynthesis to occur, so you can have oxygen. But the amazing thing about the window in the atmosphere is UV, gamma radiation, dangerous radiations are blocked out. And so the light of the sun comes right down to the Earth where oxygen can be manufactured.
Other coincidences allow just the right amount of oxygen to exist in our atmosphere, but not more.
We need a lot of oxygen. We need 250 mils of oxygen every minute. As you're sitting there, you're breathing there, relaxing, you're using up 250 mils of oxygen every minute. It's incredible. That's the amount of oxygen you need to maintain your energy levels. And to get this amount of oxygen, you need to take it from an atmosphere. And you need about 20% or so oxygen in the atmosphere to get sufficient to feed your metabolic needs.
The problem with needing so much oxygen in the atmosphere is that oxygen is dangerous because it's so reactive. If you have too much of it in the atmosphere, you can have spontaneous combustion. Fortunately, the form of oxygen prevalent in our lower atmosphere is diatomic. That means two atoms of oxygen typically combine together into a molecule. Diatomic oxygen happens to be much less reactive so long as the temperature is below 50 degrees centigrade or 122 degrees Fahrenheit.
And this allows, in fact, quite a high level of oxygen in the atmosphere without spontaneous combustion.
The properties of diatomic oxygen mean our atmosphere has just the right level of oxygen we need for living. Not too little and not too much.
If you raise the level of oxygen much more than 20%, perhaps certainly more than 30%, you'd have raging, spontaneous fires all over the place here, okay?
An equally serendipitous property of diatomic oxygen is that it does not absorb heat, which has helped prevent a massive increase in Earth's surface temperature that would wipe out life as we know it.
Oxygen is not a greenhouse gas. And that's a very good job, isn't it? Because basically, as oxygen levels increased over the last 1,000 million years from nothing to the current levels of about 20%, if it had been a greenhouse gas, forget it, we wouldn't be sitting here. In fact, oxygen absorbs no incoming radiant heat because it's a diatomic molecule. You need triatomic molecules to be greenhouse gases. So let's be very thankful that there's another coincidence here. The dioxygen is not triatomic, it's diatomic. It doesn't absorb any heat. So this huge change in oxygen levels in the history of the Earth can occur without any effect on the heat balance of the Earth. So another one of the coincidences in the properties of oxygen which allow us to be sitting in this room now, breathing this life-giving gas, okay? So it goes on and on and on. There's one coincidence after another. And as I say, as far as science is concerned, these things facilitate beings like ourselves. And you can say scientifically that in fact the universe is fit for beings like ourselves to use oxygen, right? But I mean, an obvious inference is that this is certainly consistent with traditional design hypothesis, right?
The levels of purpose built into nature boggle the mind. The same key elements and compounds which are so fit to make a self-replicating system are also fit to maintain a complex creature like us.
The same key compounds which are so fit to make a replicating system are also fit to maintain a complex entity like yourself, and they're also fit, the same things, water, carbon dioxide and oxygen, that's also fit to maintain the stability of the environment on a planetary scale. Now that's amazing parsimony. There's wheels within wheels here.
But is the exquisite design we see in the elements of nature just a fluke of natural history? Denton does not think so. He notes that carbon, hydrogen and oxygen were among the very first atoms brought into existence by the stars. Carbon is the building block of living things, and hydrogen and oxygen form water, the matrix of carbon-based life. In his words, it's as if from the very moment of creation, the biochemistry of life was already preordained in the atom-building process, as if nature were biased to this end from the beginning. Humans are privileged to live on a planet where the very elements from which we are made seem pre-planned, not just for the existence of simple one-celled animals, but for large, complex, multicellular organisms like ourselves. Indeed, according to Denton, there are many ways in which humans have been endowed with unique benefits not found in any other animal. Our brains have intellectual powers, including mathematical reasoning, that far surpass the capabilities of other animals. The physical design of the human larynx enables us to utilize a much broader range of vowels and consonants than any other mammal, facilitating sophisticated verbal communication of complex ideas. The human hand is better adapted than any other known appendage for the intelligent manipulation of the physical environment. The human body and mind seem to be optimized in a variety of ways to make us the only animal who can harness the use of fire, which opened the doors to technology. Finally, humans live on a planet that seems optimized for scientific discovery. Our clear atmosphere and location in the galaxy enable many of the observations that have fueled modern science. Humans are not only equipped with a potential for self-reflection and scientific reasoning, they were placed on a planet that allows for that potential to be fulfilled. Far from being insignificant specks living on an insignificant planet, humans are truly a privileged species, inhabiting a home that seems to have been prepared for their benefit.
In my view, discovering the fitness of the universe, the unique fitness of the universe for carbon-based life and beings like ourselves is one of the major discoveries of 20th century science and one of the major discoveries of all time in the area of design, religion, science, and all these sorts of things. The human form is something significant in the cosmic order, and that's a scientific finding. It's implicit in astrobiologists thinking about looking for carbon-based life somewhere else and looking for oxygen on a planet. The 20th century have shown that human form is not some irrelevance, not some freak of nature. It's deeply significant. For me, I can't think of any discovery that's going to come in the 21st century which could be more significant than this, actually. It's a very significant finding.